In this online lecture, we're going to review electron configurations specifically for the cations of transition metals. But before we can do that, we really need to remind ourselves about the Aufbau principle and some of these periodic properties. So first of all, I want you to think back about what is an electron configuration. So pause this video for a second and think. So electron configuration is just shorthand notation for the electron wave functions. You're describing how many electrons are in each specific wave function, your s orbitals. So wave function is another word for orbital. So it's just the notation for, electron configuration is just the notation for the electrons that exist in specific atomic orbitals or wave functions. And electron configuration is really important because it helps us understand chemical reactivity. So here's our periodic table, and I just wanted to do a brief review. It says write the condensed electron configuration for neutral calcium. Okay, so let's go ahead and do that. So remember, with the condensed electron configuration, what we want to do is we want to so for calcium, we want to start with the most recent noble gas. So in this case, that's argon. So we write the most recent noble gas in brackets. And then from that, you put the valence electron. So for calcium, it was just argon 4s2. So for neutral vanadium, here's vanadium on the periodic table. Again, the most recent noble gas is argon. So we'll do argon 4s2, 3d3. So this is often how we'll see the electron configuration. And the reason, how we knew it was 3 was it's 3 into the d block. So 1, 2, 3. And you can see this is also how this version of the periodic table from your textbook also wrote the valence electron configuration. But this is not perfect. So this is, I'm going to put an asterisk next to this because it's not exactly right, and we're going to talk about why that is. So remember from Gen Chem 1, we talked about exceptions to the Aufbau principle, specifically for transition metals. For calcium and potassium, your 4s orbital is lower in energy than your 3d. However, once you start moving into the d block and that 3d orbital starts filling, it becomes lower in energy than the 4s sublevel. So your titanium, vanadium, chromium, all the way through your transition metal block, your 3d sublevel is lower in energy than the 4s. And we know this because of photoelectric spectroscopy. So we talked about photoelectric spectroscopy in Gen Chem 1. You don't need to worry about this too much here, but this is how we know specifically what electrons are being ionized first. And it's how we know that for transition metals, your 4s electrons are being ionized or they're lost before your 3d electrons. So transition metals are important because the Lewis acid of coordination complexes are often transition metals. And so for transition metals, just like we said, this 3d sublevel is lower in energy than the 4s. So let's go back to that vanadium example. So our electron configuration for vanadium, a more accurate way to write it would be argon. And then you want to write your lower energy orbitals first. So you would do 3d3, 4s2. For vanadium, you're going to lose electrons from this 4s orbital first, and then the 3d sublevel. Let's try an ionized vanadium. So for vanadium 2+, remember that we said that neutral vanadium had an electron configuration of argon 3d3, 4s2. So if we have vanadium 2+, vanadium 2+ has lost 2 electrons. So these 2 electrons are going to be lost from the 4s sublevel. So for vanadium 2+, we're going to have an electron configuration of argon 3d3. Okay, let's look at iron 3+ as another example. So just neutral iron would have an electron configuration of argon 3d6 4s2. So we're writing that 3d sublevel lower than the 4s because it's lower in energy. And so for iron 3+, we're going to lose 2 electrons from the 4s and then 1 electron from the 3d. So iron becomes argon 3d5. Okay, so here's a little trick for determining D count. So you're going to identify the group number, then the charge on the iron, so of the ion, excuse me, so iron 3+, for example. This 3+ is indicating that this has lost 3 electrons. So one trick is to just subtract the number of electrons lost or the charge from the group number, and that will give you the D count. So let's try this again with vanadium 2+. Vanadium is in group 5. So we're going to say that our group number 5 minus the number of electrons lost is going to be our number of D electrons. We would say that vanadium 2+ has a D3 electron configuration. And then we can do something really similar here for iron 3+. Iron is in group 8. So Fe3+, you're going to take, to find the D count, you're going to take the group number 8 minus 3 to get 5. So we're going to say that iron 3+ has a D count of D5. So this is the number of electrons in that D sublevel. Just as a quick conclusion, we need to understand these exceptions to the Aufbau principle to determine electron configuration for transition metal ions. So we need to understand that how these sublevels are swapping in energy to understand which electrons are lost for transition metals.